Hello everyone, today we are going to step through the XGSlab tutorial for GSA using the EN 5522 standard. So first you can see we've already started a project in the GSA module. Here we still have our start page available. This is where you can find some of your tutorial documentation, and you can also go to the videos on YouTube to see some of the other training material that's available with XGSlab. So we'll first start by going to our project information. And here's where you can enter in some of the site information for your project and track the customer who's doing the design, maybe even the location of the system if you wanted to export it to Google Earth, for example. And because we're going to follow the GSA tutorial for EN 5522, we'll next select the reference standard using the EN 5522 down the line. And our next step in the tutorial documentation is going to the multi-layer modeling. So by selecting this icon, we can either enter in our soil model manually using this table format, or we can go to the Soil Resistivity Analyzer to use soil resistivity measurements to calculate a soil model. Here we're going to use the measurements that were provided in the tutorial documentation. I'm just going to copy this from a Excel sheet. Here we have a preview of the resistivity measurements, and when you're analyzing resistivity measurements from the field, there are some tools you can use like the automatic detection tool, averaging, and weights in order to help determine a proper soil model. Following the tutorial documentation, we're going to force this to a 2-layer model and hit the calculation. And to open up more space, I'm going to reduce my message bar by clicking this pin. And after you calculate, you can apply your soil resistivity model. Here you can see the calculation determined a approximately 55 ohm meter top layer over a 30 ohm meter bottom layer. So applying this, I now have that input into my multi-layer soil model table, and I can have a visual display of the results by going to my results group box in the soil tab. Here I am going to take a snap of the soil model that's going to be recorded for my automated report. The next step is developing our actual grounding system layout. So there are a few different ways we can do that, with the importation capability or with the drafting tools. In the drafting, we have a draw group box, and this allows us to create a grounding system. We reference from a conductor library that you can choose and edit yourself. And you can reference the various conductors in the library to draw a 63 millimeter squared conductor that's at a depth of 1 meter. And let's just make a rectangular grid real quick. And if we want to add another conductor, we can have a conductor that bisects the grid. And we typically want to start adding some sort of ground rods as well. And I can change the tag associated with this to be a rod. And I will change my description of the conductor because it has different electrical properties as well. And by selecting this vertical conductor, I'm selecting my ground rod, and holding the shift key, I'm placing this at the end of my conductor. Here this is placed, as you can see, a ground rod that is 3 meters long based off of my vertical length. And this is visually shown in the ZY and the ZX coordinate system. Now we'll go back to the tutorial and follow along with the steps to import our model. In the help desk, you can download this XGSlab template. Here is a tutorial GSA EN DXF, and the red conductor represents a grounding system that we'd like to evaluate. This is a typical substation, and with that, the grounding system is drawn two-dimensionally with the intention of being able to be printed. And we'll have to correct for this in our importation by shifting this grounding system into the soil in our model. You can see on the right, we actually have a three-dimensional tank represented by this yellow conductor. And we won't have to shift this because it's already three-dimensionally drawn in the CAD program. So let's go ahead and import this. First, we have to navigate to the directory where we've actually placed our DXF. Next, you'll want to set your scale that the drafting or that they're using for the CAD program. And then we'll start importing the conductors based off of each layer. So hitting this green plus, I'm going to navigate to my E-grid layer. That is that red conductor that we saw. I'm going to assign it as electrode 1 following the tutorial. And we are going to use a stranded 63 millimeter squared conductor. I'll give this the tag grid, and I need to shift this into the earth 0.7 meters. I also want to incorporate that yellow conductor that was representing a floating tank outside of our substation. So I'm going to assign this as a separate electrode because that tank is not electrically continuous, or it's a different network of conductors from our grounding system. We will assign a solid conductor type and use the 10 millimeter diameter for our tank's conductors. And we don't need to shift the elevation of our conductors because that was already handled in the CAD program. We also may want to know where some of the civil information, where our foundations are located or drive paths. We can do a background layer in order to incorporate some reference information that doesn't have any electrical influence on how our system performs. So by checking the background checkbox, that allows me to import conductors that don't have any effect on our actual grounding system's performance. A couple things to note is this electrode fragmentation. Following the guide, I'm going to set this to a very high fragmentation. And this is just to provide more accurate results and user customizable. If you're using a lower fragmentation or higher fragmentation, it will depend on your system configuration. Another thing to note is the connection settings. We left the automatic connection settings so that the software will automatically connect conductors that may have slight gaps in the CAD program. So here we have an output of all of the conductors that we've just imported. You can filter this list similar to an Excel list, but we want to see how our system imported. Going to my display group box, I am doing the zoom all, and we can see the blue conductor represents the grounding system that we've imported. This green is the tank, and we have the grayed out lines representing some of the civil information where our masonry fence is located and some of our foundations. Next thing we want to do is actually energize our system. Now with GSA, we're going to energize our electrode 1, which is our substation grounding system with 5,000 amps. If you are curious, you can look at the GSA FD analysis process as well. And in that module, as well as the others, you'll actually be energizing a specific conductor. But here we'll continue with the GSA tutorial and we'll hit the debug. And what this tool is doing is checking that when we import a grounding system, all of our conductor is properly connected, that we haven't imported conductors above the Earth's surface, and that they are not overlapping. And we can see in my message bar I had a warning, but my debug was successful, so I can compute my model. Now that our computation is completed, we have a new tab, this analysis tab. Going to my GPR and earthing impedance, I can see I have a system impedance of 0.3 ohms for my substation. And this is something I need to note for my fault current split. Another thing to note is that you can actually change these electrode names. So in this instance, we're going to change this to my substation electrode, and we'll call this my tank. Continuing on with the tutorial, we'll go to our split factor. Here, we're going to follow the EN5522 process and enter in our impedance of our grounding system. the fault current that is supplied by the transmission line that we're analyzing, the reduction factor, and the equivalent impedance of that earth wire or shield wire. And we'll add this to our calculation and hit calculate. And we can see that of the 5,000 amps that is being injected or available to fault our system, approximately 3,200 amps is actually going to produce a ground potential or earth potential rise at our system. So we'll go ahead and apply this to our electrode 1. And this is going to require that we reanalyze my system. So you can see the analysis tab has disappeared and we'll have to recompute. Before we do that, we'll also want to check our conductor sizing. And here we can enter in the 5,000 amp fault current, maybe a half-second clearing time. We can also evaluate other faults at the same time that could be contributing to the overall health or longevity of our conductors. So we have another fault, for example, that could produce 25,000 amps that is expected to clear within 0.35 seconds. This grid split factor is associated with the conductor if it's a down lead from a piece of equipment. This K factor will be 1 because there's only one path for current to flow. If it's actually within the grid, so in your network, you're going to have multiple paths for current to flow. And for our tutorial, we're assuming we're just looking at the conductor of our grid conductor. So I'm going to apply a split factor of 0.6, and we'll use the copper material and calculate a minimum cross-sectional area for our conductors. And we can see approximately 52 millimeters squared, which means that our 63 millimeter squared conductors that we imported are properly sized. Next, we'll also want to compute our touch and step voltage limits. So I'll zero out this value, but we have the clearing time of 0.5 seconds, no additional shoe or glove resistance, and we'll hit the calculate. And we can see that the permissible limits for touch voltages are 220 volts and 660 volts. We'll apply this and go back to reevaluating our system. We can see that there's more current leaking or more current exiting through the perimeter of our grounding system. We'll also want to look at our touch and step voltages as well as the overall ground potential rise and how that propagates in our system, in our area. Following with the tutorial, we're going to set the X and Y coordinates for our area calculation to match that of the tutorial. So we'll just need this 70 meter width here. Hitting the calculation. Now the software is going to determine the propagation of voltages along the Earth's surface. So this is all of these points that you can see are going to be locations that the software is determining the voltage that somebody's feet may be at. And that's going to be used to compare the voltage of our grounding system or the tank or other sort of metallic objects. Now that the computation has completed, we can display the earth potential. So here we're going to use the color style to display the ground potential rise. We could also change this to other types like the contours. And if you're using contours or lines, then you're able to actually export this to a CAD file that you can use for your grounding designs. We'll also want to evaluate our system's performance for touch and step voltage compared to our permissible limits. So here I went down to the touch and step voltages group box. Hitting the plus mark or the view 2D, I am evaluating my system's performance for touch and step voltages as it relates to my electrode 1. And we can look at my system performance for touch voltages. And when I'm looking at my touch voltages, this is without that red, green, or yellow mask that was displayed previously. Here we can look at the step voltages as well. We can see along the perimeter we have our worst step potentials. And next thing that's a little more accurate evaluation is we can actually change the reference that we're evaluating our touch and step voltages to. So here we've assigned electrode and electrode 1 representing our tank. We can change this to evaluate all elements, for example. Even though we're using GSA and the voltage of our electrode is equipotential, we can evaluate both the tank and the grounding system of our substation simultaneously. And what we'll find is a different plot for our permissible limits, because the voltage of the Earth's surface to our substation, when you're within the substation, is acceptable within permissible limits. And when you're close to the tank, the difference between the tank's voltage and the Earth's surface potentials are sufficient and within the permissible limits. So we'll go ahead and take a snap of this for our report. And we'll take a couple snaps of some of the previous images that we took for our touch voltages and our step voltages. Here we can go to our gallery and see some of the images that we snapped throughout this evaluation, and then go to the report where we can create our report of all of the essential data components that were used to develop our XGSlab model. As you can see, we've incorporated the soil model resistivity measurements and the image associated with that, our electrodes energization, how much current's going into our grid, and the overall system impedance. And we are also going to see our area calculations, our permissible or our safe areas plot, our touch voltages, our step voltages, and our conductor sizing calculations, split factor calculations, as well as our bill of materials. All of this is exportable to PDF, Word document, or other file types as well. This is just a sample of some of the steps taken in the tutorial documentation. You can get a more detailed view of the analysis process using the tutorial documentation to step through all of the calculations, or view some of the other videos on our website.